Okay, let's look at the solutions to the electromagnetism questions. You'll see they're all quite similar because they do ask the same things every year. Essentially, there's not too much variation on it. An electromagnet can be made from a coil of wire through which a current is passed. The arrows in the diagram below show the direction of the current in the coil. On the diagram, draw 3 magnetic field lines to show the shape and direction of the magnetic field around and through the coil. If you do notice, it does say through the coil as well there. So if we just have to draw 4 lines, essentially what I would always start with is they're generally quite parallel, and I would draw one that goes straight through the center, and then one that goes near the top, but that goes straight through the middle, and one that goes towards the bottom and goes straight through the middle, and then I would just bend them round so that they kind of meet at the other side. Okay, and there's our 2 marks for going through. That wasn't very good there, was it? For going through the center, 1 for doing the ones at the side, and then the last thing we have to do is the direction. So you use your right hand grip rule, so you use your right hand, pretend you're gripping it, point your fingers in the direction of the current, which is marked for you. They've been kind, so there's the positive side. Goes up at the back, but down at the front. And when we do that, you should see that your thumb points this way, which tells us that this is the north side of the magnet, and the field lines should be going like that. Okay. Part B, to investigate how current affects the strength of the electromagnet, it was used to pick up paper clips. Current was changed. Here's a number of paper clips that were attached. What should be added to the circuit above to allow the current in the coil to be varied? It says added rather than replaced. Therefore, I probably wouldn't go with a variable power supply. I would go with a variable resistor instead. And then I want you to draw a graph for those results. So you can see we're changing the current on the x-axis. So it starts off at 0, 0. You'd be surprised how many people don't plot that point and lose a mark. 0.5 and 4, 1 and 9. So it's kind of going in between those ones. 1.5 and 12. And then 2 and 17. Draw a best fit straight line. A little bit of variation in the points, but they're very close to all being in a straight line, so something like that, leaving a few above, a few below. Use the graph. How many complete paper clips can be lifted by an electromagnet when the current is 1.2? Well, if we notice on this x-axis, 2 squares are worth 0.1 amps. Okay, because between there and there is 0.5, so each square is 0.05. So that'll be 1.1 and that'll be 1.2. So we draw a little line up and a little line across. And for me, that's falling at a whole number, and it is 10 paper clips. Question 4, similar type question. They've got a quick curve through the center, which I don't think is exactly right. The diagram below shows a coil of wire wrapped around a cardboard cylinder. If an electric current is passed through the coil, magnetic field is created. The ends are marked north and south, so slightly different this question. On the diagram, mark the direction that the current between the points X and Y that will be used to produce a magnetic pulse. You have to work backwards this time with your right hand rule, so point your thumb towards north, so your thumb needs to point left, and then if you notice, your fingertips will point downwards in behind, which means if you kind of tilt your wrists around, you can't really see what I'm doing, they'll point up at the front. So the current is going like this, and that's the only way you could grip that and get your thumb pointing to the left, which means the current kind of follows up the ways there. On the diagram, mark the direction of the magnetic field lines at A, B, and C. Well, we know that the current flows away from north, the North Pole, outside of the solenoid, outside of the coil of wire, but it flows towards the north inside. So it's going to go like that. And this feed line is going to go like that. You didn't need an arrow there, but it's then going to coil around and go towards south, like so. Okay, so we don't need all those intermediate ones. The arrangement above is described as an electromagnet. What does this mean? A magnetic field that is created by electric current. What material placed inside the cardboard cylinder will increase the strength of the magnet? We would use an iron core. Apart from increasing the current or adding a different core, what could be done to the coil above to increase the strength? Well, the only other thing we can increase is the number of coils. So we could increase the number of coils. Okay. And 2006, another draw a magnetic field diagram. So a magnetic field can be created by passing a current through a coil of wire. On the diagram below, draw a maximum of 5 magnetic field lines. Probably go for the maximum there, although it's only worth 3 marks, so maybe 3 would do, but you may be gauged by how much time you have left in the exam, but I probably draw the 5. To show the shape of the magnetic field produced, label the polarity of each end of the coil and the direction of the magnetic field lines. The arrows on the wire and the windings show the direction of the current. So we've actually got a lot to do here for 3 marks. So firstly, draw the one that goes straight through the center. Okay, and then I would draw the one at the top and the one at the bottom. And if we're just drawing 3, that's probably enough, but I'm going to draw the 5 for completeness sake. Like so. And all we do then is we just circle these ones around. If you do the lowest and highest ones quite tight, that will give you space to bring these out and around so that they get further apart. We want it to be weaker away from the electromagnet. So there's our field lines, but we now need a direction. And once again, we use Fleming's right-hand grip rule, where that's the direction of the current. So if you imagine your right hand gripping that, fingers going down in front of the object, your thumb would point this way. So this is our north and this is our south, and therefore the field lines go away from north, like so, towards the south, and we then go from south to north inside. Okay, so I think those 3 questions are enough to show you the typical questions they will ask on electromagnets. The only other things they can ask that we haven't gone on to yet is electromagnetic induction, including transformers, but also the uses of it. So we will look at bells and relays next lesson.